Thank you all for coming along this evening. We've got 3 talks lined up so far for the next 3 weeks. Carol this evening, who I'll introduce in a minute, then David Gill next week, and then David Lomas the week after, talking about the Fen. David Gill next week will talk about the Cambridge phenomenon and why, and business around Cambridge. And then I'm still looking for a few more people. I've got a few people I'm chatting to, and I think I might do a talk as well towards the end of that. So probably we'll have about 4 or 5 in total is the idea. They may be spread out a little, but I will keep you updated with the schedule. So anyway, let's get straight on. It's a great pleasure to introduce Carol Williams, who lives in Little Wilbraham, and as she'll tell you about tonight, she is a geophysicist by training, spent a lot of time working on plate tectonics and how continental. So Carol, do tell us about your research and the subject of plate tectonics and continental drift.
Right. Thank you, Andrew. Well, good evening, everybody. As Andrew said, I was a geophysicist. I'm no longer, unfortunately. But I'd like to tell you a story of some geophysical work done in the 1960s, which, after very few years, became a revolution in the subject, and it led to plate tectonics. Now, plate tectonics is a well-known phrase, perhaps nowadays, but since most of the ideas, not most, but some of the ideas came from the department in Cambridge, where I was at the time, I'm going to tell you a little bit of the backstory. Now, of course, the manifestations of plate tectonics are volcanoes, earthquakes, and tsunamis. Things that we are lucky enough to read about and see on television, but we don't experience ourselves. And I'll come back to that right at the end. There's another minor manifestation of which we are mostly unaware, and that is every time you fly from Heathrow to New York, your journey gets 10 centimeters longer every year. And should you decide to go from LA to New Zealand, then your journey will get about 15 centimeters longer a year. So look out for it.
Too hot sitting there.
Now, if we could start with the first picture, please.
I know.
So let's just remind ourselves what the structure of the Earth is. And this diagram, there's a little plain cross-section in the bottom left-hand corner and an enlarged segment on the right. But if we look just on the left-hand side to begin with, the black line outlining the Earth, that is the crust on which we live, and it's a very small part of the total matter of the Earth. The main part is the mantle. It's orange, and in the blown up bit, it's all the orange and the yellow. And this is material which is high in iron and magnesium. It's spread, goes down to a depth of about 2,900 kilometers, as the diagram says. And at the bottom, it's very hot and at very high pressure. And the role of the mantle is to transfer heat from the Earth's core back out towards the surface. And it does this by an arrangement of enormous convection cells. Now, this isn't a liquid. It's a solid, but it's a viscous solid, so it is able to have motion. It's a bit like pitch, perhaps, that is, it's still until it's pushed by an external force. But as you can imagine, the material at the bottom, very hot, at very high pressure. And by the time it gets to the top, and it's just underneath the crust, it's still hot, and it's still at high pressure, but at considerably less than deeper down. And this has the effect of changing the nature of the material, and it becomes mechanically weak, and that's the bit that's known as the asthenosphere, and that's going to be important to our story. And below the mantle, there's the core. The outer part is liquid, and the inner part is solid, and its chemistry is nickel iron mostly. And that's responsible for creating the Earth's magnetic field. Now, you might ask, well, whatever gave anyone the idea of continental drift? Who would have thought that all these rocks we see on the land masses might be mobile? Well, we were left one clue. And when the early maps started to be made, particularly around either side of the South Atlantic, quite a number of people remarked, well, it does look a bit as if that northeast corner of Brazil might once have fitted into that angle of West Africa. Well, in 1911, the German geologist Alfred Wegener took some time to look into this, and he collected samples from around the Atlantic. And indeed, he found some similarities from one side of the ocean to the other. And the term continental drift was created. But there was no evidence for how you could have any movement, and actually the subject just became out of fashion, and the academic institutions just didn't want to discuss it anymore. But it did leave us with a feeling that we didn't really know enough about the oceans. Well, in due course, echo sounders were invented. And of course, every ship has an echo sounder now, and to stop it running aground. But they're quite small instruments with a rather weak ping that doesn't have to go down very far. So a precision echo sounder that needs to go right down to the deep ocean floor is quite a big piece of kit. And I'll tell you about the one that we used to use aboard Discovery in the 1960s. We used to tow a fish which is 4 to 5 meters long, and it was towed from a crane amidships and at a depth just below the ship's keel. And this might sound quaint, but it recorded onto our rolling paper record, and the scientific watchkeeper had to annotate the time and the sounding value by hand every 10 minutes. And then we had to look up a correction for the velocity structure of the water in that area and apply it and write that in the logbook. And in due course, when someone had worked out the astronavigation fixes of where the ship had actually been and drawn a ship's track, then someone with lots of patience used to write in tiny letters the value of the soundings at 10-minute intervals along the track. Well, nobody does that anymore, of course. But a ship going to sea on its own with an echo sounder, you're only looking at a very small swathe of bathymetry immediately below the ship. And if we go to the next picture, please, then once all these soundings are collected together, then you can get a 3-dimensional picture. Can we go to the North Atlantic picture, please? Thank you. So this is the North Atlantic without its water. And we can see several features here. First of all, there's the continental shelf, and that stretches from the shoreline out towards the ocean, it slopes gently. And at about 1 kilometre water depth, it changes character and becomes a steep cliff, which descends down to 5-6 kilometres down to the abyssal plain. At the foot of the abyssal plain, you sometimes find a triangle of sediments. It's bits and pieces that have actually fallen down the cliffside, really, and that's called the continental rise. It's not always visible, and it's quite difficult to see on an echo sounder because you get side echoes there. But anyway, this is the feature the lawyers looking after the law of the sea chose as the boundary for the nation's exclusive economic zone. The abyssal plain itself is covered in sediment. It's flat. It's featureless most of the time, though there are areas where there are more lumps and bumps. But this takes us to the left to the ocean ridge. Every ocean has an ocean ridge. In the Atlantic, it's in the centre, but not in the other oceans. And at the ridge crest is at a water depth of about 2 kilometres. And as you see, it's segmented. And these segments where the actual ridge, the crest of the ridge is offset, they're joined by something called a transform fault. And then the extension of the transform fault forms a deep valley, which is known as the fracture zone. And you can see all those stripes cutting across the ocean ridge are fracture zones. Next picture, please. Right, this is the same thing for the Pacific Ocean, and it looks quite different. It's different largely because the ocean ridge isn't in the center. It's this key feature in the bottom right-hand corner, curving round and up into the Gulf of California. And when it gets there, it converts into a transform fault, which is the San Andreas fault, the one that goes underneath San Francisco. And then north of San Francisco, it reappears for a short segment of ocean ridge again. And you can see all the fracture zones and the offset of the ridge as just as you can in the Atlantic. But the main feature I want to draw your attention to are these dark curves in the north and to the west, particularly of the Pacific. In the north is the Aleutian Trench, and the Aleutian Islands border the trench. And this isn't quite so visible in the other trenches we see, but the islands are part of a trench function and topography. So here we have, after the Aleutian Trench, we have the Japanese Trench and the Japanese islands on the side, the Mariana Trench, which is the deepest at 11 kilometers water depth, and then the Philippine Trench, and then the one in the news at the moment, right at the bottom middle of the picture, you can just see the northern end of the Tonga Trench. Next picture, please. So in 1965, Sir Edward Bullard, who was head of the Department of Geodesy and Geophysics, decided to make a computer fit of the continents around the Atlantic. And he used the University computer Titan, or thermionic, two rooms of thermionic valves of it, giving him a computing power of probably far less than we have in our phones nowadays. And he didn't connect the continents at their... Yeah? He didn't connect the continents at the shoreline, but at the 1 kilometer depth, which is essentially at the edge of the continental shelf. And as you can see, he achieved a very convincing fit. The blue and red areas are, the blues are gaps in the fit, and the red are overlaps. And as you can see, they're very insignificant. And the fact that he'd done this work on a computer made it all the more convincing. And it spurred interest once more in continental drift. And it showed, again, the need to study the oceans and the ocean floor. I mean, ships had been going to sea for centuries from the old sailing ships, and we knew quite a lot about the water. We knew the biology, the bit of the water chemistry, temperature structure, etc., something about the tides and the currents. But we knew practically nothing about the sea bottom. So 5 main laboratories took up this challenge. 3 in North America, 3 in America, 1 in Canada, and the smallest was the department in Cambridge. There were no instruments to be built, so everybody had to design and build their own instruments. They started off as electric, they soon went to electronic. The recordings were initially analog, and then they went into digital. And so there was a constant evolution in the instruments we were using. And eventually, as they became electronic, they got smaller in size, more accurate, and more reliable. And the 2 data types most useful to plate tectonics were seismics and magnetics. Now, seismographs had existed for a long time. People had been listening out for volcanoes and earthquakes. And they needed to be adapted for use on land and for the use of explosives instead of having to wait around for an earthquake. And then once that had done, the system needed to be adapted again for use at sea. And I'll just describe to you how we used to run a seismic line in this era from discovery. We'd launch a line of 6 to 8 floating sonobuoys. They're free floating. Each had a hydrophone, which is a marine microphone. And initially they had a radio and they transmitted the signal back to the ship. And after a few years, small tape recorders became commercially available. So they were put into the sonobuoy so they could self-record as well as radio the data back to the ship. We had 2 chances of getting it. Then, as the ship steamed away from the sonobuoys, we'd make up the charge. You wrap the sticky tape around lumps of explosive, put in a detonator with a long time delay, and launch it over the side. And the energy from the bang went through the rock layers below and refracted back all at every moment. And that was a signal that was picked up by the hydrophones beneath the buoys. The longer the line, the deeper the layers that were penetrated, but the larger the shot needed to be. So what did we find? Well, considering that the initial idea of the ocean bottom was just simply an extension of the strata on land, that it just disappeared under the water and came up on the other side. But we found a 3-layer model with thin sediment, weathered basalt, overlying basalt. Now, basalt is an igneous rock. It's high in iron and magnesium, higher than most of the rocks on the continents, so hence it has a higher velocity of sound. And we saw absolutely no evidence at all for the silica, lighter and less dense silica alumina rich rocks that you see on land, the shales, the clays, the limestones, etc. And we also found that the oceanic crust was quite shallow, about 8 to 10 kilometers. So first of all, our traditional thinking was completely wrong, and we had to learn that the oceanic crust was very different from continental crust. And the other useful property was magnetics, and we measured this by towing a magnetometer astern of the ship. It had to be outside the ship's own magnetic field. And initially we found a lot of high, well, not we, but several people, groups of geophysicists found high and low values of data that formed long, narrow regions, and people couldn't make any sense of it at all. But in 1963, Drum Matthews, who was at the department in Cambridge, had made a detailed magnetic survey of the ocean ridge in the Indian Ocean. And he'd made his survey parallel to the ridge crest. And he noticed that his high peaks and his low peaks were all lying parallel to the ridge crest. And he and his student Fred Vine hypothesized that new hot igneous material was being injected at the crest of the ridge, and it's pushing the older ocean crust symmetrically aside. And that, as this material cooled, the iron-rich minerals became magnetized, and they became magnetized in the direction of the Earth's current direction of magnetic field. And they termed all this seafloor spreading. Could we have the next diagram, please? So I mentioned current direction of the Earth's magnetic field. Oh, the pictures of everybody are over, Andrew, the pictures of everybody are over the pictures of the audience, over the right-hand side of the diagram.
You can either move it or make it smaller.
I can move it?
Yes, you can move yourself or the pictures of everyone.
Okay, I'll try and move myself.
but we can see it.
Okay, oh, that's fine, because the right-hand corner is the important bit. So this is a diagram of the Earth's magnetic field, the reversal timescale of it. Because, and we know this because while people were working at sea, people were also working on land on paleomagnetics and a whole number of different sorts of rock sample. And they were finding that not all the magnetization was pointing in the current field direction. Quite a lot of it was pointing out away from the current field direction. And they measured the radiometric dates of all these samples. And so they were able to make up this time scale. On the upper scale, we've got 0 million years on the right-hand side. That is now, today, and it goes back 55 million years. And the next one down starts at 55 and goes down, and the third one is older still. And the black areas are in the current field direction, and the white are in the opposite direction, reversed. And as you can see, not only are there many reversals of the Earth's field, but they are very irregular in time. And also, if you look towards the 0 point, in the last million years, there haven't been any reversals. And hence, no Homo sapien has experienced a reversal of the Earth's magnetic field, which is a bit interesting. So this is quite a difficult concept, and there were a lot of people who were very questioned all this. But if you imagine your school bar magnet with its north and south pole, and you just rotate it horizontally 180 degrees, the effect that it creates is similar to this. For those who are modeling the Earth's real magnetic field, they're using much more of a dynamo model of the liquid outer core rotating about the solid inner core. So if you want to process magnetic data, and you want to look at just the magnetization of the Earth's crust, then you need to subtract the Earth's main field. This is, if you think of your bar magnet again, and then there's an arc of line of force that goes from one pole to the other. So this can be calculated and subtracted from our observed readings, and then you're left with what we call an anomaly, which is just due to the magnetization of the crust itself. And so, and then if these magnetic anomalies were contoured, could you go to the next diagram, please? And mapped, they give us a stripy picture of the ocean floor. This was my thesis area, out of interest, and the area to the west was done by Columbia University. And if you look at to the left-hand side of the stripes, there's one that's a little bit thicker and it's marked with a 1, rather small. That is overlying the mid-ocean ridge. That's where current seafloor spreading is taking place. And that's one of the cause of the 5 centimeter extra journey time you're making to New York. So what one can do is take the magnetic reversal time scale and use that as your model. You can stretch it or compress it and calculate the magnetic profile you'd see from that model, and then compare it with your observations. And then you can work out the rate of seafloor spreading and the age of the seafloor. So all these anomalies here between the mid-ocean ridge and the continental margin have numbers and they have ages. And the oldest one here that you can see, the quite wide dominant one of Iberia, that's 80 million years. And that's when North America started to separate from Europe, Eurasia, and the North Atlantic started to form. So we'd learned quite a lot from all this. We'd learned about the features of the seafloor. We'd learned that oceanic crust was very different from continental crust. They found some evidence for magnetic reversals and the lineations that they make. And incidentally, the same pattern of lineations was found in all the oceans, which was a bit sort of convincing. We'd thought a bit about mantle convection. And then there were things, people like the Deep Sea Drilling Project in America. They drilled a number of sites down the ridge crest, and they found the depth of the basement rocks was older the further you got from the ridge crest. People were finding changes in magnetism in cord sediments, and the paleomagnetists who were doing this, finding so much interest in their work, they were making more measurements on rocks of various ages, and so they were putting more detail into the magnetic reversal timescale. But there was a dilemma about all this, about seafloor spreading, because if new material was being formed at the ridge crests, and geologists and astronomers were telling us the Earth was not expanding, then we had to find somewhere where all this excess material was being deposited. And we needed a mechanism to connect all this together. And this is where a big idea came from the Cambridge department again. In 1967, Dan Mackenzie, with an ex-Cambridge colleague, developed a kinetic theory for the rotation of a slab over the surface of a sphere, and described it as a motion about a pole of rotation. And this gave you a mathematical description of how one slab moved against another, and it could give you a velocity and a direction. And in the meantime, in the literature, a slab became a plate. And the theory predicted that there would be three kinds of plate boundary. The next picture, please. So the first one is an ocean ridge. So here you can see the new hot molten magmatic material being inserted at the center, and the whole displacing the older rocks to either side. And those grey bits that are stripes there are the magnetic directions, alternating from normal to reversed. And next one, please. So the next sort of boundary was a transform fault. So these were the offsets in the ridge which we saw in the oceanic maps. The red, if we just look at the left-hand one for the moment, the red areas are the ridges which are actively spreading, and the transform fault which connects the two sections is their connection. And this motion across the transform fault is just a horizontal strike-slip motion. So actually here we're looking at a plate boundary. So if you go down the top red bit and sliding on the transform fault and down the other bit, everything on the left is one plate and the other plate is on the right-hand side. And then there's a third sort of boundary. Could we go to the next picture, please? Well, we didn't really know much about what happened at trenches in those days. And then a French geophysicist in 1968, Xavier Le Pichon, made an approximate calculation of everything we knew at the time of spreading ridges and about how much material was being injected into the surface, and made a comparison with what might go down a deep trench by looking at the magnetic lineations that were missing or could go down the trench. And it was suggested that the third plate boundary was where you got compression of two oceanic plates together, and one would start to subduct beneath the other. And as it went down, the surface material would melt and come up and rise and form an oceanic island. And those were the islands we were looking at, particularly in the map of the Pacific. So the Aleutian Islands, the Japanese Islands, Philippines, and so on, and Tonga are all formed in that manner. So that's an ocean to ocean plate boundary. So if we go to the next slide, please, and then we're looking at an ocean continent boundary. So a continent is made up of light rocks, and it's far too light to be able to subduct. And so it's up to the denser oceanic crust is to go underneath the continent. And then is much the same thing. And so you see it going down, getting deeper and deeper. And again, the upper material melting and rising up and to form a mountain belt. This is typically the situation along the Chilean Trench, which follows the whole margin of Chile and forming the mountains, the volcanoes forming the Andes. I stood there myself and I could count 8 volcanoes, and I believe they have 200 altogether. Now these noughts and crosses on the downgoing slab are earthquakes. And as this cooler material goes down and is recycled into the mantle, it gets warmer and melts and eventually is totally absorbed and becomes mantle material. And it's thought that, oh, well, we shouldn't be able to get earthquakes down to a very deep depth. But a Japanese seismologist measured an earthquake down to 700 kilometers. So clearly it takes quite a long time for the slab to go down and for it to melt and no longer be brittle enough to create an earthquake. And the next picture, please. So then if we get 2 continents colliding together, neither of them can subduct. And so all they can do is crunch together and fold, and they form a mountain belt and uplift themselves. So this is exactly how the Alps and the Himalaya, for instance, were formed. So naturally, with all these suggestions, there was a lot of controversy and skepticism. First of all, especially in America, they'd not totally accepted the fact that you could have reversals of the Earth's magnetic field. And now they were being asked to believe that the crust was capable of all this motion. And fortunately, perhaps, it was still Cold War time. We're now in the late 1960s, and there was a test ban treaty. And particularly America was very anxious to be able to distinguish Russian nuclear explosions from earthquakes. And so funding was made available for the worldwide standardization of seismograph network. And this called for better precision, more accurate clocks. They all should have the same polarity in the calibration. And at the same time, American seismologists were paying greater attention to the first arrival of the earthquake signal. And indeed, they developed a new method of analysis. And they were able to define the first motion. And so they could distinguish expansion, compression, and strike slip. So can we have the next picture, please? So this is the distribution of global epicenters of earthquakes. And as you see, if we look along the middle of the Atlantic Ocean, there are earthquakes all along it, all along the mid-ocean ridge. And the type of earthquakes that are found there were the expansion earthquakes, right along the ridge. Strike slip, there's a lot of strike slip motion along this boundary around Antarctica, and there they are. And the compressive earthquakes were found along the ocean trenches, if we look in the Western Pacific particularly, and along the Andean belt of mountains and the whole of Western and North America. And the Himalaya India was originally attached to Madagascar, and about 75 million years ago, it started its motion northwards until it collided with the Southeast Asian continent. So this not only better defined the plate boundaries, and particularly the ones we didn't know very well, but it was very convincing. And this work also showed that a plate was deeper than we thought. It would go down to 75 to 200 kilometers, i.e. down to the asthenosphere, down to that layer of the mantle which is mechanically weak and allows some motion. So if we can go to the last slide, please. So this is a map of the surface of the Earth divided into plates. There are about 8 major plates and a whole number of minor ones. And the brown one is the North American plate. We're on the green Eurasian plate here. And as you can see, the British Isles are some distance from a plate boundary. That's why we're aseismic and we have no volcanoes. Times were completely different in a different plate configuration. In fact, in about 400 or 500 million years ago, Scotland was on a different plate to the rest of the British Isles. And so we have this motion which takes place because the Earth's crust and upper mantle is floating on this asthenosphere. And like icebergs, the lighter continents float higher than the more dense oceanic crust. And the water is incidental, but that's why the continents are mostly above sea level and the ocean is mostly below sea level. And so it's not just continental drift. There is not just the continents that move, all the crust is in constant motion. And the energy for all this is simply heat. Thank you.
Thank you, Carol. That was fascinating, really fascinating.